Our speaker is Ryan Castellucci.
Thanks. So these slides are live now if anybody wants to follow along, and the video will go up whenever BSides releases it. That's probably going to be 3 or 4 weeks. So at DEF CON 23 2 years ago, I gave a talk called Cracking Cryptocurrency Brain Wallets. As part of this talk, I released a tool called Brainflare, which cracks Bitcoin private keys that were generated by using SHA-256 of a password or passphrase. This found a rather shocking amount of stuff, but that's not really what this talk's about directly. What I want to talk to you today about is how to make this really fast and how to make it even faster for some other types of weak keys. So since DEF CON 23, I have added a bunch of new modes to Brainflare, special case optimizations. I added support for a bunch of hardened algorithms. It has Ethereum support now, pay-to-script hash support, raw private key input so that you can write external tools that generate keys and feed that in. You can feed raw pay-to-script hash scripts in there, and Bitcoin's gotten a little bigger, so the Bloom filter has actual false positives now. So there's a feature for making sure that those false positives are caught and ignored. So let's talk a little bit about Bitcoin keys. Bitcoin uses the elliptic curve digital signature algorithm with curve parameters called SECP 256K1. This is from Standards for Efficient Cryptography, which is a document that Certicom put out a while ago that standardized a bunch of elliptic curve parameters. The P stands for prime field, 256, it's a 256-bit field, and K is Colbert's type of curve, and I don't actually know how that is special, but Bitcoin is the only application that widely uses one of these curves. With this curve, you have points represented on a curve that satisfy the equation y squared equals x cubed plus 7 in a finite field over a large prime. It's slightly larger than 2 to the 256. And then private keys are integers in a different finite field. You don't need to know that number, really. And then public keys are formed by multiplying a private key with what's known as the base point. This is also the point that you get for a private key with integer value 1. And if you want to go from public key to private key, you need to have an algorithm that can efficiently find the discrete logarithm. This is supposed to be very hard without a quantum computer to run Shor's algorithm on. There's some stuff in Bitcoin that makes it so that this is a limited risk even if somebody does have a big quantum computer and wants to crack Bitcoin. I don't have time to go super into detail on how elliptic curve cryptography works. There's a paper linked at the bottom of this slide that you can read. This is what Bitcoin's curve looks like plotted over real numbers. It's actually run over a finite field, so it looks like noise, but this will be important in a minute. For key generation, you can basically just generate an arbitrary 256-bit value and it'll work. 32 random bytes. It works fine with most software unless you choose 0 or N, which is that long number that ends in 4141 hex. This makes it really easy for people to write applications that generate keys with weak randomness or do clever things like brain wallets. Bitcoin uses something called Bitcoin script. When you send a payment in Bitcoin, you are sending a payment to whoever can redeem a program, whoever can provide inputs to a program written in the Bitcoin scripting language that makes it return true. There's a couple of really common scripts that are used. Bitcoin has addresses to represent these. You have the addresses starting with 1 that just represent payment to a hash of a public key. This RIPE-MD 160 of a SHA-256 of some value is what Bitcoin calls hash 160. This is interesting because if you pay to one of these addresses and the recipient never reuses it, even if quantum computers are around, the public key isn't revealed until it's spent. So unless the quantum computer can crack it in about an hour, it'll still be okay. There's also pay to script hash, where you are sending to a hash of a script. Don't worry too much about that. Ethereum uses the least significant bits of the output of Kashek, which is the hash algorithm that became SHA-3 with slightly different initialization parameters, because Ethereum was released a little bit just as that was being standardized. And Bitcoin actually has two different representations of public keys. There's uncompressed, which has both the X and Y coordinate, and compressed, which has the X coordinate and a header byte that indicates whether it was even or odd, which is equivalent to indicating whether it was positive or negative. If you recall the graph, you saw that it had 2 points at each X value. So you need to know whether it's the top or bottom point on the curve. But once you know that, you can compute the Y value. I have a lot of general optimizations in Brainflare. Most of it is pretty boring standard C optimization. Minimize memory copies, inline functions, allocate all of the memory at startup because malloc is slow. Statically initialize buffers for values that don't change much or that are partially reused. I decided I wouldn't bother implementing any sort of threading because message passing is a pain in the ass. So to make sure it was still efficient, there's external data files you load in that have, for various purposes, and those get mapped with shared memory, which if you run this on Linux will ensure all processes trying to access that file just get pointed at the same chunk of memory. So you can run however many copies, they're all loading 20 gigs of files into RAM, but it takes 20 gigs regardless of how many copies you run. SHA-256 for brain wallets is important. It's also used in anything that's looking at Bitcoin addresses. So Intel put out a bunch of assembly implementations of SHA-256 using instruction set extensions on Intel processors. There's actual SHA-256 instructions on some of the newer processors, and then there's the AVX2, AVX, and SSSE3 instruction sets, which are also faster, and there's fallback to C implementation. Only the transform function is implemented, and you can't incrementally fill in the hash because none of the stuff that Brainflare does needed to do that. I would love to find optimized versions of RIPE-MD160 and SHA-3 Kashek, but I have not yet. So hash padding. Hopefully some of you know how hash padding works, but in short, you have your data, you follow it with a 1 bit and a bunch of 0 bits, and then the length of the input of the hash. This is so that if you have two similar values that differ only in that they have a bunch of nulls at the end of them, you get different hash values. So there's a bunch of static buffers in Brainflare that have that all computed already. And then to speed things up a little more, SHA-256 output is written directly into the pre-computed buffers for RIPE-MD160, so no copying is required there. Here's what one of those buffers looks like for RIPE-MD160, which is little endian, whereas SHA-256 is big endian, which is kind of annoying. And then here's what this looks like in use. And then here's one where it's doing hash 160 supporting an arbitrary length, but the caller has to take care of all of the padding. And then here's what that looks like with a compressed public key. You get you have padding, and you put the public key in there, and you feed it into this, and it works great. Other fun things, you can attack multiple cryptocurrencies at once. If you want to do that, you need to post-process them because there's nothing in the data structure that will indicate which cryptocurrency it came from. But I've played around with getting address dumps for 100 random altcoins and feeding them all in together. It works perfectly fine. If you have ones that use different public or different address formats like Ethereum, you can still do that. You can reuse the public key computations, but if you wanted to do, say, brain wallets on Ethereum, nobody really used SHA-256. They used Kashek instead. So the public keys you calculate aren't going to be helpful. But if you wanted to, say, search for keys matching a bad random number generator, you could do that. If you wanted to incrementally search for all the keys starting with 1, you could do that too. So as far as public keys go, Brainflare's got a flag that lets you specify which transforms you want. These are stored as function pointers with a type identifier. Uncompressed, here's an example. This is uncompressed key. It's just hashing the public key. For a compressed public key, there's a little bit of bit twiddling to extract out whether y was whether y was even or odd, and again just gets fed into the hash. Ethereum uses Kashek instead. We take the last 160 bits. That's the address. The other one is truncated X coordinates, which are interesting if you want to look at the signature nonces. A Bitcoin signature has as inputs a nonce value, which must not be reused, otherwise bad stuff, and the private key. Essentially, the X coordinate of a public key created using the nonce as the private key is one component of the signature, and then there's another component. And don't worry about it too much. Then if you want to look for pay-to-script hash stuff, you can do that. Really? Is that a drill, or are we getting out? Okay. Great. Carry on here. All right. Before we get into some of the mathier bits here, I wanted to briefly mention that there are some pretty serious differences in speed between the different operations you can do on an elliptic curve. Adding 2 field elements, super fast. Multiplying 2 field elements, pretty fast. Doubling a point, fast. Adding 2 points together, it's all right. Inverting a field element, kind of slow. Multiplying an integer by a point, which is deriving a public key, that's about the slowest part. So let's talk about point multiplication. The naive method is just to, this is, if you can read that, great, but otherwise.
Pardon me, for one moment, I apologize for the rudeness. I just want to make sure that the connection is good.
It is.
It's flickering a little bit, that's all.
Yeah, yeah, the screen's going to flicker, I guess.
Sorry about that.
Sorry. Right, so you start out with the base point. You add it to an accumulator. If your bit is 1, double it. If the next bit is 1, you add again, and so forth. This is pretty standard. But this can be made a lot faster with a partial pre-computation. Again, here's what that looks like in a academic paper. And here's what I came up with after staring at the explanation in the paper and the code for a while. You set up a 2D array of points. You fill the 0th column with the points for 0 through 2 to the n minus 1. The 0 point is not actually the 0 point, it's the infinity point, but when you add it to something, you don't change the value. I don't know why this is, but it works. And then you fill out the rest of the row by multiplying it out as necessary. So this turns your your point multiply into basically a bunch of lookups and adds. Memory usage is about as you would expect. The code I've currently got takes 88 bytes per entry, so that's that. And this is limited in large part by RAM speed rather than CPU speed because you're going to be missing every cache. You're going to be missing the cache every time. libsecp256k1, which is the elliptic curve library for this curve that was written by a bunch of the Bitcoin people, does this already with a 4-bit window, which is fine. It only takes up a little bit of memory. Brainflare, when it starts up, does a 16-bit window, which is significantly faster. Most of my actual testing I do with a 24-bit window, which takes about 16 gigs of RAM and yields a 2.5x speed up. Bigger windows use more RAM. You quickly hit diminishing returns. There's a paper about how this works. A grad student named Song at University College London wrote this code for me, and I integrated it into Brainflare, and you can read the paper there. Okay, so the next thing is affine versus Jacobian coordinates. Affine is the simple XY representation of a point. Jacobian adds a Z value and uses this Z value to do tricky things that make the math faster. This is all well and good, but the Z value does not stay 1, and so when you want to convert, you have to divide, and well, dividing in finite fields is actually kind of tricky. I'm going to go very quickly through these slides because we were interrupted, and it's not super important. So 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 1, because modular arithmetic. If you want to look up finite field arithmetic and modular arithmetic, please do so. I don't have time to explain it. The tricky part is division. So the way we do division is instead we multiply by the reciprocal, or as it's generally called when doing this sort of math, the inverse, the multiplicative inverse. So given, if you want to divide, if you want the inverse of x, given x, you find y so that x times y equals 1. So in our 5-element toy field, this is the table, and don't divide by 0 because that's bad. Here's some examples. So to convert our Jacobian coordinates back to affine, we need to do division. To do division, we need to find the inverse of the z value. Finding the inverse is very slow. But we can cheat with algebra. So instead, we take a bunch of z values, we batch them together, and we do one inversion for the entire group plus 3 multiplications per z. This is a lot faster. In brain wallet mode, it's a 1.7x speed up. If you're doing incremental mode, it's actually a 16x speed up. So very much worth doing. It took me a while to understand this very well, but here's a quick example. So we have 4 values we're batching. We multiply them together, keeping each progressive one because we'll need them in a moment. Then we calculate one inverse of our last value. Then we, oh, that slide got slightly messed up. That 3 is supposed to be at the end of the first line. I don't know how that happened. So now we cancel some stuff out. So we want the inverse of z3. So we take z0 times z1 times z2 and divide it by the inverse of z0, z1, z2, z3. And everything except for the 1 over z3 cancels out. Then we cancel out the z3 term in our temporary variable. and then we repeat this to get all of the inverses. Right, helpful. Other thing that we can do to make things faster is just not give a shit about side channels. Older versions of the library didn't put much effort into avoiding side channels because nobody was supposed to use it for anything real. And then they went back later and fixed all of this stuff up. So I just use the old version that is faster but completely unsafe to use for any real work. So on my to-do list is to actually implement all of the algorithms that I can implement in timing unsafe ways to make things faster. Can also do some special cases. Brainflare's got an incremental mode, which takes advantage of the fact that key pairs are homomorphic for addition. What that means is if we take the pub key of the sum of two private keys, that's the same as the sum of the public keys of those two private keys. And adding public points together is much faster. So if we want to go through one of them, instead of incrementing the private key, computing a new public key, we compute a starting private key, and then we take the equivalent public key for one and just add it over and over again really fast. And then the most recent fun thing that I did was keys from a byte stream. So if you've got a shitty random number generator, say somebody decided that a good way to generate random keys was to use the JavaScript math.random function and turn it into a byte and call that 32 times. Well, if you wrote something to generate that key stream, you could feed it in this way. It's about twice as fast as feeding in raw private keys. The way this works is we build two tables, one for subtracting the most significant byte, and then another for adding the least significant byte. And we go through, subtract the most significant byte multiplied by 256 by doubling 8 times. There's a slightly more efficient way to do this where I can just multiply by 256, but it's a pretty marginal improvement, and I haven't had time. And then once we've done that, we can add in the new byte. There is a bunch of tricky special cases that have to be done for this. There's some invalid private keys that if you're, say, doing a forensic search of Bitcoin keys from a RAM dump or a hard drive dump, you'll get lots of strings of zeros, which are invalid keys. So that has to be detected, and fix-ups must be done. Or if you get all 1 bits, it's a little weird, and you can't keep adding like this. But it's not really a big deal. I actually found some really weird things dumping my hard drive into this. There's a lot of random Linux binaries that have SHA-256s of random strings embedded in them for some reason. Also, for some reason, a SHA-256 of some default picture that comes with Windows 7 was in there. I have no idea why that was there either. I have some more examples that I will go through at the talk I'm giving with Marie later, where we analyze terrible brain wallets and the people who steal from them. Anyway, so this is a little easier to understand with an example, perhaps. So here's a starting key. Just ignore the fact that this is not the right size and is only one value. Just pretend that this has a corresponding public point. Okay, so we have the value. We subtract off the top byte. We multiply by 256, add in the new bottom byte, and then do this again over and over again, feeding through whatever it is you're looking at. So in order to do searching, Brainflare uses a Bloom filter. There's There's a couple 100 million addresses that have been used in Bitcoin since the beginning of time. Bloom filter is a data structure that allows you to check for set membership efficiently as long as you're okay with the occasional false positive. It's pretty quick. The way this works is you have hashes of some input value that are used to turn on a bit in a large bitmap. And then to check, you just check and see if all of the bits that correspond to your input are already set. And if so, you have a hit or maybe a false positive. And you can calculate the odds of a false positive for a given data set. The thing is, though, we're looking at hashes of Bitcoin public keys and public keys themselves, and these are pretty randomly distributed. So we can just take different combinations of that and splice it together and call that a hash, and that actually works fine. So here's some ugly macros that do the whole thing. The way this particular algorithm works is it takes the public key as an array of 5 32-bit values. There's a couple of hashes that are just take one of the values, and others that take certain parts of one of the values, bit shift them around, and OR them together. And again, this works perfectly fine, except for that now that Bitcoin has about, I think last time I checked, it was getting close to 300 million addresses since the beginning of time. The 32-bit Bloom filter with 20 hashes starts to have a lot of false positives. So I am writing some new code that works around this problem, which looks like this. I wrote a Python script that actually generated this. I didn't type all of this out by hand. But I went through and found combinations of shorts, 16-bit values out of the hash value that I could combine together into a 48-bit value. And the 48-bit value is nice because now I can use a bigger Bloom filter, and as long as the Bloom filter is still a power of 2, all I have to do is and mask out the extra bits that I don't want. And as far as false positives go, here's what it looks like today. This is about a 1 in 1,000 false positive rate, so that if we're searching, I think the current performance, if I'm doing brain wallets, is about, on my PC, is about 550,000 per second. So there's 550 false positives per second. So we need an efficient way to find those and not spam with them. So normally, if you've got an array that's ordered, you use a binary search, right? Because a binary search is log n, and that's pretty efficient. If you don't know what a binary search is, here's a quick walkthrough of one. You seek to the middle. That was too high, so we'll seek to the middle of the first half. That's too low, so we seek to the middle of the second quarter. And that's too high, and then we seek to the beginning of the third eighth, I believe that is. And we get a hit. That's 4 operations. That's pretty good, right? But if you've got a huge list of these, that's still kind of bad. At almost 300 million, that's going to give you, what, 18? Yeah, about 18 hits. So instead, there's another algorithm called an interpolation search, which works really well if you have a unified distribution within your search range, which tends to happen when you have a bunch of hashes. So this does have the disadvantage of if somebody is able to pass you crafted inputs that are specifically designed to ruin your day, you will be very, very slow. But as long as that doesn't happen, it's log n, which instead of 18 operations would be 4 or 5 to search all nearly 300 million addresses. In practice, it's a little bit worse than that because it tends to be front-weighted, but overall it works pretty good. And so here's what that looks like. Another good way to explain an interpolation search is, say you've got a phone book and you're looking for someone whose last name is Williams. You're not gonna just look right in the middle because you know they're closer to the end. So you open the phone book towards the end and refine from there. And that's how an interpolation search works. So here it's gonna estimate based on the list. If we're looking for 5.1, it should maybe be about there. And the algorithm will say, oh, well, that's slightly too high. Let's try jumping back a little bit. And it gets it on two guesses instead of 4. Okay, I have a little more time than I thought, so does anybody want me to revisit the finite field arithmetic and actually explain that? Yeah. All right, that's a little quicker than I thought I was going to get through this, but any questions? I can go into detail on other stuff if people are curious. Got a question over there? I also wanted to, I really hope this is obvious to most people, but cracking Bitcoin addresses and taking the money if it's not yours is kind of a dick move and probably illegal, although I talked to a bunch of lawyers about this and all of them had a different opinion on which law it broke. So, yeah, let's see. I had conversion, trespass to chattels, Computer Fraud and Abuse Act, and a couple of other things. But yeah, if you do something and it's obviously it should be bad and you get caught, you'll probably have a bad time. Anyway, question?
Have you thought of using minimal perfect hash functions?
Scoobs, is that you?
Yeah.
Yeah.
For instead of the Bloom filter, it requires a lot of work.
Yeah. You should submit a patch, Scoobs.
The exact.
Yeah, the Bloom filter works. It's reasonably fast. If somebody wants to give me some other code that is faster, I would be happy to accept it. Yes?
I was just curious if you had any, I thought you'd have graphs showing how much you've actually sped up. I understand, the basic stuff you're describing, but I was just curious, what did it actually, work out to be if you had, test data?
Yeah, so I've done some benchmarks, but the problem is a lot of these are mode dependent, and a lot of times the optimizations you'll get a speed increase from the optimization, but the thing you optimized maybe sped up 50 times, but your overall performance only increased by 10 or 20% because of all this other stuff you're doing. Like that's why it's, for example, when I put in the assembly implementations of SHA-256 and tweaked that stuff to use pre-padding and all that stuff, I only got another 2 or 3% because the calculation time was dominated by generating the public keys. So, and the other thing is the speedups are not in isolation. So like the pre-computed multiplication plus the batch defined conversions don't necessarily, when used together, have the same effect as you would compute from both of them in isolation, if that makes any sense. So yeah, I don't have great graphs. I'm sorry. So the as far as performance goes, the original cracker I wrote back in 2013 using OpenSSL and no tricks whatsoever did about 10,000 per second on my computer. Then the first version of Brainflare I wrote did 130,000, and my current code does 550,000 keys per second. And this is all Bitcoin with SHA-256 brain wallets checking both the compressed and uncompressed version.
Cool. That would have been a real pretty graph.
Sorry.
Questions, anyone? What's your opinion on web-based wallet generators like bitaddress.org?
Tire fire?
Makes sense. What's the most secure way to generate a wallet then, offline or otherwise?
It depends. I mean, it's the key generation is very simple. There are tools where you roll a bunch of dice and hash the dice output, and that gives you a private key that is probably reasonably safe. But really, random number generators are actually pretty secure. You can trust them. There's offline wallet tools like Electrum, which will give you a 128-bit seed represented as 12 words. You can memorize that. Nobody's going to crack that, although if somebody wanted to, they could certainly try. It is deterministic. But yeah, and bit address, which you specifically mentioned, like they use decent crypto libraries to power that thing. Browsers now have actual cryptographic number generation built into them via the get random values API. That's pretty secure. It also mixes it, like it has you wiggle your mouse around on the screen before generating anything, and that helps too. But I don't know. Major web browsers, probably okay. Don't recommend, but probably okay. And then there's a lot of weird web browsers, and I've actually even seen, I think it was some video game console web browser I was playing around with. I got two different ones to generate the same values with the cryptographic random API. So don't generate Bitcoin keys on a game console.
Thank you.
Questions? Hi, I was just wondering, does Brainflare get impacted in any way with the bit 148 that's coming out?
The which?
Bit 148.
No. So there's no SegWit support, if that's what you're asking about.
Yeah.
I honestly haven't really looked into segregated witness and cracking that. I haven't seen any software that generates keys that work with segregated witness in a stupid way, but I'm sure somebody will eventually figure out how to do that. I tend to add stupid key generation schemes to Brainflare as I find them. Actually, when I was checking into some things to make this slide, I found another one from Ethereum that did something dumb, which I'm going to implement probably next week. By the way, not all of the stuff I've mentioned in these slides is in the version that is currently on GitHub, but I will have that out by next week. There was an attack I ran that found a wallet that had a balance that's currently worth about $1,500 in it, and I was advised not to include details on how I did that in the talk, and so I am ripping that code out. Yeah, if anybody has a wallet with 0.64 Bitcoin in it that they generated a while back and has my weird-ass Bitcoin address with no uppercase letters or numbers other than the leading one in there, yeah, you should move your Bitcoins. Because yeah. Yes, that will work. Wait, no.
Thank you. That's a lot. No sleep for you then, huh?
I get some sleep.
I remember you talking a different talk about repeat K and other things.
Yeah. So Brainflare can crack bad nonces. The K is the nonce value. I briefly mentioned this, but you have a 256-bit value that if you reuse it, you can compute the private key. There were some bad wallets out there for a while that poorly generated K values, which led to reuse, but it's clear that there's probably other issues that could be replicated with it that could perhaps be used to break some keys. But 99% of the stuff I try to find keys, I will crack keys and then find that somebody else already ran that attack because I think there are a bunch of dudes out there who have just decided that their job will be stealing Bitcoin from people with bad keys. Again, I think those people are assholes, but they're very busy, I guess. And I'm sure some of them have GPU accelerated tools that are way faster than mine that they will not release. Right, anyone else?
What are your plans for future improvements?
So I would really like to learn how to do GPU coding and get that nice acceleration done. That's the main one right now. There's also, as I mentioned, like the incremental mode is not incremental. The key stream search mode is not completely done. I want to try some silly stuff like, what if I feed it RC4 with a blank key? Oh, hey, that actually came back up on the screen. Silly stuff like that. Really, the Bloom filter implementation needs to be replaced. There's maybe something more efficient that I can do besides a Bloom filter. I don't know.
How much money do you estimate you've saved from hackers?
That's really hard to say. And that's mostly the subject of the talk that Marie and I are giving at, I think, 2 p.m. today.
Is that 2 p.m. or is that the one in 14 minutes?
That's the one at 2 p.m. according to the schedule.
How many talks are you getting?
Just, I mean, it's mostly her talk. I just cracked a bunch of passwords and provided data.
Or will there be charts in that talk?
Yes, there will be charts in that talk.
So everyone go do the 2 p.m. one.
Yeah. I don't know. So the talk I gave at DEF CON got this site brainwallet.org, which was kind of infamous. Also because there have been allegations that the guy who ran that site was actually cracking brain wallets himself, and he refused patches to improve the security of the system. And really, that was the site that used math.random as key generation for a while. So there were all sorts of sketchy things about that. And that got shut down for my talk, and that has probably saved some people. I've seen a few posts on Reddit like, oh, I saw this talk, I moved my money out of a brain wallet. There's also, like, I found brain wallets that clearly weren't pilfered, and that's always interesting. But some of those were from before my talk, because I was definitely not the first person in the security industry to say this was a terrible, terrible idea. And I'm disappointed that some of those mistakes got repeated at Ethereum. I had a conversation with somebody, I think sometime last year. He had an Ethereum wallet that had 46,000 Ether in it, which at the time that I talked to him was worth $500,000, and currently I think Ethereum's about $200 a piece. So is that $8 million? Yeah, the key was Guybrush from Monkey Island. That was the password. All lowercase. I don't even know. Like, I feel really bad for that guy. Probably.
What are some of your favorite passwords that you found?
Well, so there's a woodchuck on my shirt because one of the passwords I found was, one of the first things I found was how much wood could a woodchuck chuck if a woodchuck could chuck wood, which when I found it had 250 Bitcoin in it. And I actually managed to find the owner of that and explain to him why this was a terrible idea. And he was very grateful.
Any questions?
Yeah, we have another talk in 10 minutes in this room.
Sorry, not in 10 minutes.
Okay.
It's at 2.
Okay.
So was there anybody that gave you a bounty? You told them that their wallet was insecure. You gave them a pointer, and then they gave you a tip.
Yes, the woodchuck guy gave me 2 Bitcoins, and I gave them to a friend as a wedding gift. And if I recall correctly, he said he eventually sold them for $1,700.
Very nice.
Ready? Anyone else? Last chance.
Right.
Best practices to protect yourself from this sort of attack?
Use the standard software and not some random dude's website that says it's totally secure. Because it's probably a trap.
I think that's pretty good general advice, too.
Yeah.
All right. Well, thank you, everyone.
Yeah.
Thank you, Ryan.